In this video, we'll use first derivatives to find maximum and minimum values of a function. Introducing a definition critical value, C is a critical value if f prime of C is equal to 0 or f prime of C does not exist. And the point C, f of C, is a critical point. So we have two cases here. First is f prime of C is equal to 0, and the second case is f prime of C does not exist. Let's look at the first case here. F prime of C is equal to 0. What happens to the graph when f prime of C is equal to 0? We know the derivative of a function gives us the slope of the tangent line, right? If the slope of a tangent line is 0, that means that tangent line is a horizontal line. And when you have a horizontal tangent line, you have these four cases. In the first case, there is a local maximum. You can also call it a relative maximum. At the highest point, this f prime of C is equal to 0. And on the left of this C point, you can see the graph is increasing, and on the right of the C point, the graph is decreasing. That means the derivative of the function on the left of the C, just in this little area, is positive. Right? On the right, the derivative of this function is negative because the slope is negative. Right? And in the second case over here, you can see this graph has a local minimum, and the graph is decreasing to the left of the point C and increasing to the right of the point C, meaning the derivative of f of x in this little area is negative, whereas the derivative of f of x in this little area, a little bit greater than C, this little area is greater than 0. Negative, positive. Right? Now for the third case here, the graph is decreasing on the left side of C and also decreasing on the right side of C. So that means the derivative of f of x is negative a little bit on the left side of C, and a little bit on the right side of C is also negative. For the last case, the graph is increasing on the left side of C and on the right side of C also. So the derivative of f of x is being positive on the left side of C and positive a little bit over the right side of C. So when f prime of C equals 0, only the first two cases will give us local maximum or local minimum. That is when the derivative of f of x have different signs on both sides of C. And when they have the same sign, negative, negative, or positive, positive, there are no maximum or minimum. Let's look at the other case. So if we have a continuous function and f prime of C does not exist, your graph may have a cusp or a corner or a vertical tangent. And similar to the previous four cases, the derivative of f of x has different signs on both sides of C. For example, here's negative, positive, or here's positive, negative. Then there is a local maximum or local minimum. And when it has the same sign on both sides of C, for example, here both positive, here's both negative, then there are no maximum extreme values. There's no maximum, local maximum or local minimum. Let's look at one example. For a function g of x equals negative x cubed plus 12x minus 22, find the critical values and sketch the graph. No critical values happen when the derivative of f of x equals 0 or does not exist. So let's find out what f prime of x is here. All right, sorry, here's g. G prime of x equals negative 3x squared plus 12. Right? Okay, we make that equal to 0. So make the derivative of g of x equals 0. So we have negative 3x squared plus 12 equals 0. We'll solve for x. Here we'll get our critical values. So we have 3x squared equals 12, x squared equals 4, so x is plus or minus 2. So here we have two critical values. One is x equal to 2, the other one is x equals to negative 2. You may ask, well, what happened to does not exist? Well, if you look at g of x, it's defined everywhere. There's no case when the derivative of g of x does not exist. So we will only look at the case when it's equal to 0. Now we will use these two critical values to help us find relative maximum or relative minimum. So first we'll draw a number line. Okay, let's put these two values here. So since it's a number line, the small number on the left, negative 2, the bigger number on the right, 2. As you can see, these two numbers, these two critical values, are cutting our number line into 3 different intervals. And you can see here is negative infinity to negative 2, negative 2 to 2, and 2 to infinity. We know f prime of negative 2 is equal to 0 and f prime of 2 is equal to 0. We just did the calculation. Now, out of these 3 intervals, we're going to pick a test point or pick a representative from each interval. And we'll use that test point to check the sign of the derivative of f of x. Sorry, it's g of x here. If that test point is making the g prime of x positive, then the whole interval will make g prime of x positive. Similarly, if that test point is making g prime of x negative, then the whole interval will make it also negative. So let's put a test point from each interval. So for this interval, I will choose negative 3. Here I will choose 0, and over here I will choose 3. Okay, I'm going to plug in negative 3 into g prime of x, which is, go back to the problem, which is over here. Negative 3, and so I will write it here, negative 3x squared plus 12. All right, so negative 3 times negative 3 squared plus 12. And this is, well, overall it's negative, right? Plugging 0, it's positive. Plugging 3, it's going to be also negative. So what does this negative, positive, negative mean? That means during this interval, your graph is decreasing. Sorry, it's negative, right? And in this interval negative 2 to 2, your graph is increasing, and between the point 2 to infinity, your graph is decreasing, right? So that means negative 2 is a local minimum, whereas 2 is a local maximum or relative maximum. And let's use the information we got to graph to sketch this function. All right, at the point of -2 and 2, we have a local maximum and local minimum. Let me calculate where the critical points are, where the local maximum and local minimum are. So g of -2, let's do the calculation over here. G of -2 is actually, plug it into g of x, you have -38. So that means your local minimum is at -2. Okay, let's say it's here. Let's say this -38 is totally unproportional, but let's say this is -2, -38. That's your local minimum. Okay, and your local maximum is 2g of 2. Let me calculate over here. G of 2 equals, G of 2 is -6. So let's say this is -6. I know it's not proportional. Okay, so here's 2, -6. All right. Okay, so our graph is, decreasing. I'll use a different color. So it will, from -infinity to -2, it's been decreasing, right? And then when it arrives here, and then it starts increasing, and then at this point, okay, and at this point it's decreasing again. So this is how your graph roughly look like. Now let's look at another problem. F of x equals -2 over x squared plus 1. Find the relative extreme points and sketch the graph. Right, to find the relative extreme points, we need to know what is f prime of x. So we'll find that first. That will be -2. Okay, we will see this as -2 times x squared plus 1 to the -1. Right? So the power rule, move the -1 to the front, then you have x squared plus 1 to the -2, and then times the derivative of x squared plus 1. Okay, so organize this a little bit. This is a 2. This goes to the bottom. And what is this part? That is 2x, right? So multiply to 2, that's 4x. We'll check when f prime of x is equal to 0 or f prime of x does not exist. Right, first of all, f prime of x, if you look at the denominator x squared plus 1 will never equal to 0. So this case, so f prime of x will always exist, right? There are no undefined points. So let's just look at the case f prime of x equals 0. Well, for this fraction, or this rational expression to be equal to 0, if and only if the numerator is equal to 0. So that means the critical point, or the critical value is x equals to 0. Okay, now let's check if 0 gives us a local maximum or local minimum, or neither of those. So let's put 0 on a number line. 0 is cutting the number line into 2 intervals. One is from -infinity to 0. The other one is from 0 to infinity. We're going to take a test point from each interval. What do we want to test for? We want to test if the test point is making f prime of x positive or negative. Right. Okay, so test point -1 here, and for this interval it's 1. All right, if you plug in -1 into f prime of x, which is over here, the bottom is always positive, right? So overall it's negative, and when x equal to 1, it's positive. All right, so if you look at this case, you're having the graph decreasing from all these intervals, and then, the slope becomes 0 at x equal to 0, and then increasing. Right, so that means we have a local minimum or relative minimum at x equal to 0. Okay, with this information, let's try to sketch the graph. Just a rough sketch. So we have x equal to 0 over here. Well, it's not at this point actually. I want to find where this local minimum is. It's 0, f of 0, which is 0, 0, right? Is it 0, 0? Sorry, I'm plugging into the wrong function. I plug into f. I plug into f prime of x. Plugging into f, you have -2 over 1, which is -2. Okay, so it's 0, -2. Okay, 0, -2. Let's say it's here. Mark this a local minimum. Then it's decreasing to the left of -0 and increasing to the right of 0, and that's roughly how your graph look like. But if you want to be a little bit more accurate, you can kind of tell from the equation there is a vertical asymptote here. So that means as x goes to -infinity and infinity, your value tend to go to 0. So it's kind of like this to be more accurate, because you have a y equals 0, a horizontal asymptote here. Let's look at one more example. Find the extreme points, relative extreme points, and sketch the graph. We know we have to find the derivative of f of x, right? That is, derivative of -5 is 0, and derivative of x to the 2 over 3 is 2 over 3 times x to the -1/3, right? If you rewrite it, that will be 2 on top, 3 at the bottom, and at the bottom it's cube root of x. And if you take a look at this expression, that will never equal to 0 because the numerator is not 0, right? And the bottom can be 0, so that will make f prime of x undefined. So f prime of x does not exist when x is equal to 0. So that means 0 is our critical value. Okay, so let's see if this critical value will give us a local maximum or local minimum, or neither of those two. 0 here, 2 intervals, -infinity to 0, 0 to infinity, test point. So test point. And sine of f prime of x. So test point here, I'll pick -1. Here I'll pick 1. So let's check. If you put -1 in the f prime of x, that will give you a negative number. put 1 there, will give you a positive number. So that means your graph will be decreasing during the left interval. Then it will become undefined, maybe a cusp or a corner, and then or increase. So 0 here gives us a local minimum. Okay. Sketch the graph here. Where is this critical point? That is at 0. Plug into the original function. That's 0, -5. Okay, 0, -5 is where our local minimum is. -5, let's say it's here. Okay. And your graph is decreasing on the left of 0 and increasing on the right of 0. This is roughly how your graph looks like.